Hello guys, welcome to part 2 of the Intro to Calculus series. And well, I'm assuming you've watched part 1. So I'm going to try and introduce a new idea about calculus. And this is what I believe is the second most important concept here, and that is derivatives. Now, I'm going to try and teach this intuitively once again. So just bear with me. Try and look at this line here. From first sight, this looks like a straight line. I mean, that is what it looks like. If I zoom out enough, you can see it's not a straight line, it's a curve. If I think, well, that's obvious. I mean, you zoom in enough to any part of a curve, you're going to get a straight line. It kind of just makes sense. After all, a curve is just, well, it's not really a bunch of straight lines, but it kind of just does make sense. But on the other hand, you might also be thinking, no, because no matter how much you zoom into a curve, it may look like a straight line, but it'll never actually be a straight line. And sure, this idea is quite open to interpretation, but this is the main idea behind derivatives. And, well, we're going to try and approach this with limits once again. As I said, that is the cornerstone of calculus. But before all that, I do want to give a better explanation for derivatives than zooming into a curve. Now, before I explain exactly what I mean by this little zooming in kind of thing, I'm going to first start with an introduction to point slope form. I mean, it's not really introduction, it's just a refresher. You probably learned this in Algebra 1, but just want to just refresh it once again. So say we have 2 points on the coordinate grid, and I want to find a line that connects them. To be specific, I want to find the equation of the line that connects them. So there just happens to be this line goes through these and connects them like this. So how would we do that? Well, in algebra 1, the way it's learned mostly is we say, okay, the equation for the line will be y minus um the y coordinate of one of them. Just say this one is just x1, y1, and say this one is x2, y2, x2, y2. And so y minus y1 equals m times x minus x1, where m is the slope. How do we find the slope? Well, we have these points, right? This is rise over run. So it's y2. So the slope is going to be y2 minus y1 over x2 minus x1. So this above will be the equation. And this is what m is. Alright, so now that we know what point slope formula is, let's go back to the graph and try and see what we can find. And then I'll show you what I really mean by this zooming in thing. So there we are. We have x1, f of x1, x2, f of x2. And so the equation of the line connecting them is going to be y minus, we're actually not going to care about the equation. Remember, we're trying to find the slope. And so we're going to come down here and we're just going to try and find the slope. Just simply the slope. So how will we find the slope between these 2 points? I mean, well, it's pretty easy, right? You can just do f of x. And you know what we're going to do here? We're going to actually rewrite this. Since we're trying to find the limit expression, we're going to have as less variables as possible. So you know what we're going to do? Do x2, alright? What we're going to rewrite this as is x1 plus some value h. Yes, I understand we just added a new variable, but we also removed one, so it's fine. You might be thinking, well, what's the use? Alright, so the y coordinate is going to be f of x1 plus h, right? Okay, now we have a new set of coordinate points, and now the expression is just longer. Alright, let's just do it. So now, what's the slope once again? It's y2 minus y1, so f of x plus h minus f of x over x1 plus h minus x1. Oh, and also notice something. x1 plus h minus x1. The x1 and x1 just cancel out. So we can just rewrite this as divided by h. Alright, now we have a more general equation for, hold on, this next one. So now we have a more general equation for like the slope, but given some value x1 and some incredibly tiny value h. Because remember, we want these 2 points to be as close together as possible on the function. And we guarantee it's on the function because we use f of x1 plus h. F can be any function actually. So this time we're actually going to make f of x be a very simple function, say x squared. Alright, x squared, a very simple function here. So now, we have a general, well, not really an equation, more formula, I mean, you'd say, but we want h to be a very small value, right? Otherwise, we won't get that accurate of that kind of thing we're looking for when we zoom in really close. But the better idea, to be very exact, we can say quite literally the limit. Alright? The limit as h approaches 0. This is the key. We are letting h get closer and closer to 0. Remember, we can't actually reach 0. Because you can see down here, look, there's an h down there. We can't divide by 0. And so, this is exactly what we did in the last video. We're approaching an undefined value, even though we can never actually get there. But this time, it's helping us try and find something. Right. So now that we know a little general equation kind of, let's try and use this general equation to try and figure out what it would look like for f of x equals x squared. So little rewriting this general equation here. The limit as h approaches 0. Oh my god, I'm doing this off-centered. Alright. So now instead of using f of x plus h, we're going to quite literally just plug it into the function. So we're going to get x plus h squared. Why? Because it's f of x is x squared. So f of x plus h, or x1 plus h. And then we add x squared, right? Sorry, we subtract x squared. This is important. We divide once again by h because that hasn't changed from our f of x. So now what? Well, we're going to now try and evaluate this limit slightly more rigorously, kind of the way we did it last time, just by manipulating the function into a way so there is no denominator. So let's try and do that. Well, let's first expand the top part of this expression. So I'm just going to show the expansion of the top part of this expression. We're going to get x1 squared, remember this is x1, so we're going to get x1 squared plus 2x1 h plus h squared minus x squared. The whole thing divided by h. It's a crucial detail to remember though. You can see we're adding an x1 squared and subtracting an x1 squared. So well, we can just cancel those out. So let's see, we can rewrite this expression here as 2x1h plus h squared over h. You can rewrite this again though. Look, we can factor out an h from the top side. So we can get h, the whole thing, times 2x1 plus h divided by h. Remember, these h's cancel out. So we just get 2x1 plus h. So there it is. We've rewritten it the best we can. The limit as h approaches 0 for 2x for 2x1 plus h. Now, when we plug 0 in, h is no longer undefined. Yes, we've done legal actions to this function and created such a function where plugging 0 into h is no longer undefined. So let's just plug 0 into h. Well, since we're adding 0 here, we can say it's 2x1. I want to remind what we just found. I want to just remind you of what 2x1 really means in the thing that we just found. Because, well, where did we start though? We started with this limit expression, right? Where we said the limit as h approaches 0 for the slope. And so we made h approach 0 because we wanted to find the slope at that particular point, given we plug in some x1 value. So if you think back to what we did in the graph, we put some x1 value, say 1, and then we let the other point approach the other point and saw that it slowly approached 5. Well, this time it's a different function, it's x squared. We found something quite cool here. If you look down, what does 2x1 mean? Well, this is what happened after we fully evaluated the limit, which means this thing and this thing are the exact same. We no longer have to try and do processes like let h approach 0 or stuff like that, because we've completely evaluated the limit and found that at any point x1 we can always find the slope of that tangent line by just plugging in 2 times the x coordinate of that point. Now that makes no sense. I'll go back to the graph and show you what I really mean. Alright, so we're back in f of x equals x squared. Alright, now we're just trying to see, alright, is a slope equation of just 2 times the x value really accurate? Well, let's try and see it. Alright, so for, say, x equals 2, alright? What we're trying to do, when we zoom in, the curve should kind of look like a straight line. And that straight line should perfectly pretty much match with our equation right there. So 2 times x, I'm sorry. Okay, so we know slope, right? The slope is going to be 2 times the x coordinate we chose. Since the x coordinate we chose is 4, it's 2, slope will be 4. Because remember, our little f prime of x kind of equation is just 2x, right? That was our equation. F prime of x. Well, this is probably a nice way to introduce it. F prime of x is just a function that gives us the slope of that tangent line at any point. And by putting the limit and keeping x1 as still a variable, we didn't plug in anything for x1. And so after all our algebraic manipulations were done, we found out that for the function f of x equals x squared, we found that this function is a new function that gives the slope of the tangent line at any point. That function is just 2 times the x coordinate of the point. Which, don't you think that's a bit surprising? I mean, if you just zoom into a curve, you can see a straight line, but who expected that straight line, the slope of it, and the actual function to have such a simple relationship? I mean, both just really simple functions. Nothing complicated, nothing big. Simply a linear function. The slope of this of this f of x squared increases linearly. That is crazy. I mean, this is like one of the big things that Isaac Newton found that sparked calculus, and this is why we still study to this day. Now, if you don't see any real life application for this, I'll show you a real life application for calculus probably in a later video after we learn integration, because integration probably has some of the more um limit concepts and all, just like this one. So we can kind of see a lot more about this. But let's just test this out for now. The slope here of that line, x1 is 2, is supposed to be 4, right? So the slope is 4, but there's a problem. We found the slope is 4, but we don't know the equation. We just know the slope. Remember something. We just we know the point that we're supposed to put the line on, right? It's 2, 4. So we have that point, 2, 4. Oh, that's enough. Just do y minus y1, which is 4, equals x minus x1. Well, x1 is just 2. Oh, but of course, we have to multiply the slope by the whole thing. And look, this does not just look perfect. As we zoom in, the orange line just more and more closely resembles exactly what the blue line was showing us. And at some point, it's just indistinguishable. I can't see the blue line at all. So, well, that shows something. But here's the thing. It doesn't just apply to this. M, right, is f prime of some value, say x1, right? And here's what else we're gonna do. We're also gonna make, instead of y minus 4, we're gonna do y minus y1. Y1 is just f of this x1, and this 2 is just going to be this x1. So what did we do? We made x1 a slider, and we put an actual y1 over here. We made the slope actually be our little function we found here that represents the slope of the tangent line. This might be slightly hard to grasp. You can kind of see how at each point it's slowly capturing the slope. All you really have to think about it is, as you zoom into the line, the slope of that line is trying to reach, it increases linearly in the f of x equals x squared. And these are just some of the things in calculus I just find amazing. And it was just like quite a long video, but I do want to show one final thing. That is a trick to find this f prime of x function, this derivative. This is what a derivative is. So we're trying to find the derivative function for any polynomial. And this is just a trick to do it. I might show the intuition behind this trick later in another video. But for now, I'll just show you exactly how this is done. So say we are given an arbitrary polynomial, x to the fourth plus 2x squared. Remember, the trick I'm going to show you only works for polynomials, plus 4x, alright, minus 2. Now here are the rules, alright? Firstly, we're going to put this in terms of x everywhere. Instead of 2, we're going to do 2x to the 0th. It's the same thing, since x to the 0 is just 1. Now, we're going to have to take each term separately in the polynomial. Say x to the 4th. And here's what we're going to do. We're going to bring the exponent over and reduce this exponent by 1. So we're going to get 4x cubed. Because we reduced this exponent and moved the original exponent over. Alright? But I'll show you the intuition later, because we don't have as much time in this video, since it does take some time to show the full intuition behind this. To be specific, if I have x to the n, I will do, to find the derivative function, I would do n x to the n minus 1. Now, this is a slightly more complicated thing about than just moving the exponent over and reducing the exponent by 1. Alright. So, the first part of the expression we found is 4x cubed. Okay, so 4x cubed. What's the next part? Alright, now let's consider the 2x squared part of this. Now, what we're going to do is to put the 2 aside like this and get the x squared over here. And we're going to move the exponent over and reduce this by 1. So 2 times 2x to the 1. Alright, nice. So 2 times 2 here is 4. And x to the 1 is just x, so 4x. Alright, nice. And I want to also notice something. Remember how we said the derivative function for x squared was 2x? Well, you could find that in the same way. Just bring the exponent over and reduce this exponent. So 2x to the 1, and anything raised to 1 is just x. So, well, it's just itself, so 2x. There we go. Simple. In seconds, we found the derivative. So now, if you want, try out the next one by yourself. We have 4x this time. This is not the same 4x as this. We made this to be the derivative. So 4x, what would be the derivative of that? Find it the same way. Remember, this is 4x to the 1. Alright, I'll show you. We bring the 1 over, so it's just 4 times 1 times x to the 0th. And anything to the 0 is just 1. 4 times 1 times 1, which is just 4. Then we add, well, what's the next thing? Alright, we have 2x to the 0th, right? Which is 2x, but like, let's keep it like this. Bring the 0 over, so we get 2 times 0 times x to the negative 1. But wait, we're multiplying by 0. This whole thing just turns out to be 0. So we just add 0 here. Since we're just adding nothing, we can just completely ignore that stuff. Since we're just adding nothing. So there we are. The derivative expression for this, the derivative expression for x to the 4th plus 2x squared plus 4x minus 2x to the 0th is 4x cubed plus 4x plus 4. Remember what we mean by derivative. It's that function that gives the slope of the tangent line, which is what happens when we zoom in. At any point on the function, we just plug in our x value and we find the slope of that tangent line. So we know for a quartic, it increases like a cubic. And for a cubic, it increases by a quadratic? I mean, if you want, take in a cubic and test it out yourself. You will see that it does increase like a quadratic expression. And all quadratics increase in slope linearly. And this does have some real life applications, as I showed you. As I told you. And I will show it soon enough. Maybe in the next video, who knows. And so, if you do want to get notified for the next video, well, I suggest you subscribe.